All right, so Lauren and I are doing a high altitude balloon lessons learned. So many times we we come here or other places and we see the cool video and all the wonderful things that happened. But if you're like me, and my wife will tell you, I kind of like to learn things the hard way and unfortunately do more than I'd like to.
No!
And she's yelling, no! So we're going to do a little presentation about our most recent flight that we did. And lessons we learned from that. So this isn't going to be so much about all the successes, it's about some of the challenges and things that we learned along the way. So for who we are, I'm Mike, KD2EAT. By day, I'm an IT administrator at Cornell. By night, I'm the advisor for the Amateur Radio Club. And I've been a high altitude balloonist since I've been licensed, about 10 years. It's been my main interest. I've got about 20 HAB flights that I've done on my own and about 15 PICO flights. Lauren, would you like to introduce yourself?
Yep. Hi, I'm Lauren. I'm a rising sophomore at Cornell, and this was my first balloon launch.
Cool. So the radio club at Cornell, most of the students are not especially interested in talking on the radio. It's just not a thing a lot of the younger students or the college students want to do. But there's a great deal of interest in digital communications, in balloon flights, and we've had a great partnership between the HAM Club and both the Earth and Atmospheric Sciences Department, who want to do sort of weather-related studies, and also with the Space Sciences Department and the Space Systems Design Studio, where they would like to do some flights to prototype different CubeSat things or communications things they're planning to do for CubeSats and things. So we've had a lot of collaboration with both of those schools. So we had a flight this spring, and we intended to fly 2 payload boxes. One was one of my payload boxes, which originally I was just going to fly some cameras. But because of the pandemic and the fact that we couldn't allow students to come to the launch or really participate that much, we decided to recycle a live streaming box that I've used for a previous flight, where we live streamed video from 1.2 gigahertz, and to stream that video directly onto YouTube to sort of give the folks who worked on the project some live feedback to what was going on with the flight, because basically my wife and I drove off and launched the balloon and chased it. It gave the opportunity for the students to sort of participate. So they actually went to town and had a YouTube live stream, and we had a couple of hosts back on campus, and they were bringing up tracking information and sort of following the flight along the way. But we had a million technical problems. Along with the live stream box that I flew, the Space Systems Design Studio Alpha CubeSat project had a solar sail that they wanted to test deploying at high altitude, and Lauren's going to talk about that. So that was the second payload box that was in our string. Let's see, and we set up a couple of video receive stations. We had 2 mobile, one at the launch and landing site, and one each, and one fixed at the university ground station. So the results of the flight was a comedy of errors. There were just so many problems that day. It was just everything collided to cause trouble. And I guess at the end of the day, if you walk home with your payload box, you call it a success. So by that standard, we succeeded. By most of the other standards, we failed. But we learned a lot along the way. So during the flight, we had very limited tracking and telemetry. We had difficulty with the trackers. We had no received video from the live stream payload box at all, which had worked like a champ in a previous flight. The CubeSat solar sail payload did not deploy properly, so we sort of didn't get the video of that we had hoped for. Just a ton of problems. So I like to think when things like this happen after the fact, when I'm calmer and my blood pressure is better, that from suffering comes wisdom. So we had a lot of wisdom to gain from that flight. So a couple of the things that I did wrong, and I apologize, I don't have a whole lot of pictures of things here. I'm more kind of wordy. So we used, we had a number of tracking systems on the flight. I think all told we had about 5. Our main tracker is an APRS tracker that I've used many, many times. It's a 10 milliwatt tracker, so it's one of the little peach trackers that I build. And it worked fine right up until the flight. Before the flight, we did do some integration testing. We literally took our payload boxes because I'll say that we were concerned that the 1.2 gigahertz payload box was on the top of the string with the solar sail payload below, and we have a helical antenna aimed down. And we were concerned that we were basically spraying the payload box below us with 1.2 gigahertz signal, and we might be interfering with things. So we did integration tests to the extent we could. We went out in a field and we laid the payload boxes out, and we aimed the helical antenna at the space payload, and everything worked. The trackers worked, everything worked great on the ground. The day of the flight, not so much. So the main tracker, I think that the mistake that I made with that one is when we tested it, I had it sitting right beside our video box. On the day of the flight, I duct taped it to the lid of the box. However, the antenna was sort of draped down and hanging, and I suspect that was part of the problem because basically we had a GPS lock on the ground, but it never changed after that. So that tracker was beaconing the same coordinates every minute for the entire flight. It never reestablished the lock, and just because of the poor coding, even though it didn't have a good fix, it was broadcasting the last thing it knew, which was the launch location. So our primary tracker basically didn't work the whole time. So the lesson learned from that is be more careful with our integration testing and make sure that the tracker is basically exactly where it's going to be in the payload when you fly it, because in this case, moving that tracker just a little bit and setting up slightly differently on the payload box totally changed the behavior. So that's a pro tip. Learn the hard way. Our secondary tracker, I think my mistake there was I was spoiled by GPSL a couple years ago in Kansas. We had people running multiple receivers on different frequencies, and I decided foolishly to run my backup tracker on an alternate frequency. And it worked fine throughout the entire flight. The difficulty was that I was the only one listening for it. And it's a 10 milliwatt tracker, and when it got downrange a little bit, I wasn't receiving it. And so although we were getting good beacons and locations for it while it was in line of sight of me, as it sort of went away, we stopped receiving that telemetry. And so secondary tracker sort of fell off the map for a while until I drove back underneath it and we started receiving telemetry on the descent. But I got a little bit behind the payload, and so we didn't have very good tracking data from that one. In general, this is kind of a neat idea in our area where there's not a lot of APRS going on. So because these 10 milliwatt trackers are very weak, there's times when it lands on the ground, and even if I can hear it faintly, I can't quite decode it. But if I can drive around, and I've done this a few times, drive around a little bit until I get closer to the tracker, if I get close enough, the signal will be stronger and it'll decode, and then I'll get the final coordinates. And I consider it a feature, not a bug. That's a bit of a fox hunt. I enjoy having to have some skill about tracking. So I could put a 5-watt transmitter on my payload box and not have these problems. But to me, that sort of takes the fun out of it. For other people, they don't want that anxiety about not finding the payload. For me, half the fun is having some skill about locating it. So that's I understand the difference there. So in my situation, in this case, it was a bad idea for me to run that receiver on an alternate frequency, or that transmitter, unless I had a whole bunch of other receive stations, and I didn't. So my lesson learned there is, don't run an alternate frequency unless I absolutely have to, or unless I have a lot of additional receive stations. The infamous u-blox 12,000 meter issue, airborne mode. Those who are familiar with the u-blox GPS modules know that you have to send an initialization string to them to go into airborne mode. And if you don't send that string, it won't basically operate above 12,000 meters. I had code in my primary and secondary tracker that I've used for years that does that just fine. And I ported it over and used it in a new tracker that I created. So my tertiary tracker was using this code base. And that same code was in a tracker that Lauren used, or in a device that Lauren used for altitude checks in their payload. And unfortunately, what I discovered after many hours of debugging is that the u-blox GPS chip needs a little bit of time after you power it up before you send it that initialization command. And I literally had a logic analyzer plugged in and was doing all sorts of testing to figure out what happened. And the other funny part about it was that when I had tested before flight, I had done a lot of testing to make sure that initialization code was working. I had put, you know, a pound-defined debug GPS around some code which, when I was debugging, would actually set the mode in the GPS and then query it and make sure it was properly set. And when I had it in debug mode, it would show that it was properly set. But when I turned off debug mode, it wasn't being properly set. And it turned out that just by happenstance and sloppy code that I wrapped inside a pound define, there was a delay statement within my debug that was delaying for 300 milliseconds before I sent the command. And if I turned off debugging, that delay command was commented out. So basically, that was what was breaking the code. And I believe Lauren just lifted the subroutine I gave her and said, trust me, and stuck it in her code. And in fact, our friend Max here used the same code in a payload that he launched this a couple weeks ago, and exactly the same problem. So finally, I dug out my logic analyzer and figured out what the issue is there. So lesson learned is that, you know, test code can kill you, can hurt you if you're not exactly sure what's inside your test and what's not, inside your debug statements, and that there are subtle timing issues that you can run into based on being in debug mode versus not being in debug mode. So things to watch out for in your payloads. So I had a tertiary tracker based on a TTGO T-beam. It's an ESP32 device, and that it's a really nice little device. It's got it's got the microprocessor, it's got GPS, UBLX GPS on it. It's got a LoRa module. It's got Bluetooth. It's got Wi-Fi. It's got a kitchen sink attached to the bottom. Oh, and it even has a battery holder for a LiPo battery. So it's a device that I'm interested in using or developing as a tracker. So I flew that as a tertiary device to just test it, sending LoRa and using LoRa packets and sending GPS coordinates and LoRa packets. And that worked pretty well, except when I hit the 12,000 meter problem, which basically gave me bogus coordinates after we got above 12,000 meters. Again, this also suffered from the issue that I was the only one receiving the LoRa traffic, so it wasn't especially useful as it got downrange. But the final issue I had was I had a little OLED display, one of those little 1-inch OLED displays on there, and I was displaying the GPS coordinates on the OLED as well, just as a sanity check, so I could power on the tracker and see it right there on the screen without even needing to pull out a radio or anything. And in all my testing at home, it all looked just fine, but I didn't realize that the GPS coordinates were overrunning the end of the display, and they were wrapping around in such a way that it basically garbled the coordinates. So when the tracker landed, or when the payloads landed and we started searching, the LoRa was the first thing I started receiving as we got closer, because the LoRa transmitter is 100 milliwatt. And it was displaying coordinates in my LED display, which I trusted. And due to another comedy of errors, the other receive station I had for LoRa, which would have put it on the APRS map, wasn't working. The battery died. So the coordinates I had in my OLED, I ended up typing into a phone, literally, to try to find this payload, and it wasn't working because the coordinates were garbled. So if you're using that kind of a display and you're going to count on those numbers, I guess make sure you don't have word wrap problems was my little lesson learned on that. But that tracker, I think, is going to have really good potential once I go through those little issues. So we did have quite a go around trying to find the final location of this thing, because I was still 10 miles away when it landed, and we didn't have very good telemetry. And it was actually pretty interesting. We had the video payload. We had a person, our friend Sam. She was near the landing zone, and she was scanning the skies with a helical antenna trying to pick up the video for the landing video at least. And she managed to pick it up briefly. And it turned out she had the best set of coordinates for where the lowest coordinate. She had it at 4,000 feet. And so what we ended up doing is taking Sam's computer, and she had recorded, bless her heart, she recorded the video on her computer as the thing was coming down. And we literally played back the video and freeze framed it at the last possible frame before it went into static. And on the screen, I had the coordinates in the video. And we used those coordinates to get to the last known location as it was descending. And when we drove under those coordinates, then we started getting LoRa traffic and other beacons. But even being there, I couldn't hear my 10 milliwatt trackers because there was a berm in the field between the payload and my car, and the 10 milliwatt trackers.
Ja, Stefan, ik hoor u.
Whoop, somebody's not.
Kijk een keer naar de chat. Er staat een link in de chat. Doe een keer de chat open. Ja.
Whoever is not muted. Okay, I'm not saying who's not muted. Oh, there we go. Okay, so we weren't receiving. Whoops. We weren't receiving the final location from the APRS trackers. The LoRa tracker was giving us bogus coordinates. So there was a rock block device in the space sciences payload, which was recording coordinates, and it was beaconing, but it turns out that those coordinates aren't very accurate. So that wasn't working. So we ended up driving around in circles for quite a while. Actually, my wife had spotted the payload early on from the side of the road, and I insisted that that couldn't possibly be it. But she was right. I was wrong. And we finally used the video again with a video receive, and since it's a very directional antenna, we were able to tell, yeah, that's got to be the payload over there. Lessons learned there with those final location problems at the rock block, which we thought would be pretty useful because it gives you coordinates. Those aren't very accurate coordinates. It's sort of like Whisper. I think it's within some kind of a grid square, but it's not very accurate. And with 5 devices transmitting coordinates, it was still a chore to find the payload. And again, some of that I bring on myself because I like to use those 10 milliwatt transmitters. But you know, due to the comedy of errors we had and some assumptions we made about the rock plot being accurate, we made it a little tougher on ourselves.
I have a comment about the rock plot.
Go ahead.
The actual coordinates from the Iridium network are done by a Doppler measurement from the satellite networks themselves. So it's plus or minus about 3 miles. Sometimes it's right, pretty close, but it's not very accurate. So what I do on mine, I developed an Iridium modem that I actually have a GPS, a U-blocks on it, and then it sends the data stream to me through the short burst data modem. And then I've got it, and then I just port it through a Python program directly to APRSFI. So I've flown that at GPSL before, and it works really well. It works on the ground, but the key is the little helical antenna, which is a $60 antenna, by the way, that screws onto it, really makes a difference. So if you want to let me know, and I can tell you how to improve the Iridium modem stuff.
Cool. Yeah.
And it's bidirectional. You can send a command to it. We released a paper airplane with an Iridium modem. We sent an email, and 8 seconds later, the command was received in the balloon at 80,000 feet, and it released a glider.
So yeah, we'll talk about that because that was our intention for the rock block. And yeah, we were sending telemetry back via the rock block, but the one bit of telemetry that didn't occur to anybody was to put the GPS coordinates in there. We could have easily done that, but didn't. Not that it would have mattered, I think, because we're having GPS issues. But okay, so that's what we learned from there, and I think we might be on to Lauren's, if I'm on the correct keyword. Oh, this one was very funny. So on campus, we have a very nice ground station on top of one of our buildings with an Azel rotator. And I had written some Python code to receive the APRS packets from the APRS network and aim the antenna in that direction. So the intention was that as the balloon flew, across the horizon, we would be aiming this antenna, which had a high gain helical on there to receive the video. Well, a couple of problems. Number one is our primary tracker was beaconing, as I said, after launch. Every minute it was re-beaconing the launch coordinates, and they never changed. So the antenna at campus aimed itself at the launch site and stayed there. When the secondary tracker was being received by my car and gated up to iGated, it was great. The campus antenna would aim itself at the payload, and then within a minute, the primary tracker, which had the wrong coordinates, would re-aim it. I had it listening to both. And so for a while, the ASL rotator was going back and forth between the bogus tracker and the tracker I was receiving, until I stopped receiving the secondary tracker, at which point the campus rotator just went and pointed at the bogus location and never aimed in the right direction again. And I guess it's fortunate that after a while, the script also crashed. So the rotator just didn't even rotate anymore. And which is probably good, because that poor motor hadn't really been used much at all. And then for the span of about 30 minutes, it was running pretty much full duty cycle, going back and forth between the two sets of coordinates it was receiving. So a lesson learned there, following two trackers was maybe not the best idea, especially if these trackers have a history of sending bogus coordinates. My original thinking was, well, if one of the trackers dies, at least I'll still receive the other. And the other one was, unfortunately, that ground station is all the hardware and software is in a secure location in the building that only I had access to, and the students did not, which made it sort of difficult when we started having problems with it to figure out, because I was driving my car well away from campus, and after a bit, I did, by phone, get Lauren logged into the ground station to look at something when we realized the code had crashed, at which point we said, oh, good enough. But that took a long time. So lesson learned there is a couple things. One is we had a number of ground station issues as well, that we would have been better served to have more people who could get access to the ground station and fix things. But we were also pretty short-staffed on this whole thing, between just people with access to get to the places on campus that they needed to get access to, and because of COVID restrictions, the number of people who could be out in the field with my wife and I doing things there. So it was just sort of a tough situation all around. All right, and at this point, we're going to throw it over to Lauren to talk about her payload box and the objectives of what they were trying to do.
Yep. So I'm a member of the Alpha CubeSat team at Cornell. So basically, we're just a 1U CubeSat. And the goal of the mission is to deploy a 1 meter squared light sail with a chipsat on each corner. So basically, we'll have a rock block on the main device, which you can see is like being held on the left. And then we're also able to hopefully transmit data from the chipsats. And where kind of like the high altitude balloon launch team came in, and we were really grateful to work with Mike and the Ham Radio Club, is we kind of just wanted to test out the rock block a little bit more. And we wanted to capture some images of the light sail, because, unfortunately, downlinking images from space is a slow and unreliable process. So we're hoping from a balloon, it would be a little bit better. Yep. Yeah, so our goals were basically to trigger a burn wire from the ground via a rock block uplink. So we actually wrote our own library for the rock block. There's kind of like the Iridium library, and we rewrote that so that it's constantly checking the serial monitor, so that we can update our sensor values in between checking the rock block serial. And then we also wanted to receive telemetry from the rock block during flight, including altitude, and helpful to include some GPS coordinates in there as well. Mike, is there any way you could press the video on the left?
Sure. So here's the deployment.
Yep, so this is it deploying on the ground. So this is what we were hoping would happen during the launch. And then this is just some of the video footage, or a photo from the actual launch itself. Yeah.
So the camera was positioned, you see these cameras on these balls, they were positioned looking up so that the sail would sort of fly out here, and it would have been gorgeous to catch the sail in a view just like this.
Yeah. So some of the lessons learned, and there were a lot of them, is that this was a pretty complicated payload that was hard to construct. And ultimately, when we were designing it, we were hopeful that students would be able to go to the launch site and help construct it. But it ended up that we were not able to go, and it was just Mike and Jules who had to set up the entire payload. So we had these kind of like fragile legs that had to be constructed, and there was this huge long checklist. And ultimately, because it was so long, it led to some things being forgotten. Like we had a camera cover left on. Not that it really mattered because the light sail didn't deploy anyway. And also each individual battery pack, we had a battery pack for each camera and also for our microcontroller, which was a TNT 3.5, had to all be turned on, and it was all packed inside this like tiny little payload. And because everything took so long to set up with just 2 people, and we needed to, so the light sail itself, the best temperature for it to deploy is 70 degrees Fahrenheit. So we had to add hot hands last minute to the payload to achieve this temperature. But that meant that, the payload was just sitting there with hot hands heating up the inside of the styrofoam container for like 20 minutes at least. And then also the rock block GPS coordinates are inaccurate, which is something we discovered. We just had like the patch antenna on there, so that probably contributed to it. Yep. So we basically had some pretty major communication problems. So the GPS struggled to get a fix on the ground. We were never able to get a GPS fix the day of the launch before launching. So, and also, as Mike mentioned, the code for the airborne mode was incorrect. But we felt okay going ahead with the launch just because the GPS was supposed to be a backup. We were meant to deploy the light sail itself through the rock block communications. So we actually did get a GPS fix back on the ground, which is why it would have been helpful to include the GPS coordinates later on. So you can see this is just like a screenshot from like the Iridium website. So you can see the first transmission is a downlink from the rock block, and it has like the altitude, which mission mode it is in. We had a photoresistor on there, and then just like a few other items. I think one of them is how many milliseconds the rock block is downlinking. And then we also had the attempted uplink that would deploy the burn wire and deploy the light sail. Yeah, so you can see that basically we were able to communicate with the rock block and before launch, and then the entirety that it was in the air, we were not able to get any communication to the rock block. And then once we hit the ground, the rock block got communication again, the light sail deployed on the ground, and we had GPS coordinates. So there's probably a few reasons why this happened as far as the rock block not working. We think maybe it was because it was directly below the video payload, the direction of the antenna, the type of the antenna, moisture. I was looking through the videos of the launch again, and it looks like we hit some hail on the way up. And then also like maybe some kind of airborne mode not being set in the rock block, or just general lack of insulation around the rock block because it was just on top of payload. That's all I had for that slide. So next steps, definitely more rock block testing. We're thinking about putting the rock block on an airplane just to check any kind of airborne mode or anything like that. And it's also like another test we can do before doing another balloon launch. And then in addition to having the GPS as the backup to deploy the light sail, having some kind of timer or another sensor. I think that's the last slide.
Yes, it was. So that was the foils that we had. So as you see, we had all kinds of problems, probably mostly from, as Bill points out in the chat, EMI noise coming from the video payload, which unfortunately was sort of a last minute, not last minute, but sort of a change of plan from the original, which was just to launch a camera payload. So we sort of shot ourselves in the foot with that video thing. So those were some of the problems that we had, and we just love to open it up to comments or questions at this point. We didn't really take a whole long time here.
Yeah, very complicated and interesting payload. Great project. I will say that in my experience with Iridium modems, the patch antenna is not as good as the helical coil antenna. I bought ones that are a little stub rubber duck, but it's actually a helical antenna for the rock frequency, which is very close to the GPS frequency. And it works upside down, sideways, any orientation, whereas the patch on the rock block really needs to be up towards the sky. The rock block is just a serial modem. You can treat it just like a modem. The commands that Iridium, there's a lot of weird commands there if you try and read through the Iridium documentation, but there's only some that are just useful and the other ones are totally useless. And what we did was we took a Delorme inReach, which is the Iridium, has an Iridium modem in it, the 9602, SBD 9602. And we tapped into the serial lines to see what it was sending. We figured the inReach Delorme engineers would figure out the useful Iridium commands, and sure enough, we found out which ones they used, and we just basically copied that, and it worked great. So, but I would keep it well away from any digital cameras, keep it in, or shield it, or make sure it's on the top of everything, it has a clear view. But we've had very successful flights with the Iridium modems that are the same type that's in the rock block, and they work great. And we have, like I say, you can send a command to it, and we've had that work successfully too. So I'll be happy to be in touch with you all and help out with any advice on that.
Yeah, that would be great. I think if we do another launch, we'll definitely switch to that other antenna. I know for the for like the actual CubeSat, we have to stick with the patch antenna. But yeah, thank you.
Yeah, and I suspect.
Just a word from.
Oh, go ahead. Go ahead, Mark.
Mike, I have had a lot of luck with LoRa trackers. I haven't done a lot of HAB stuff recently, but when I have, I've used the last time I did it, I used the Adafruit LoRa 433 modules. They're 5.3 grams, and it was super easy to throw together or something. And what was really good about it is it landed on the ground and kept on working. It was on a hill, and it had so much system gain that I was able to find it. The VHF system was just totally dead. The APRS system was dead, but I had perfect copy to track it down on the ground. So I think that's really a good way to go.
Yeah, the LoRa, I mean, those modules are rated for 100 milliwatt, which is, 10 times what I'm doing with my APRS trackers. And you can kind of customize the data however you want to. Certainly, Dave Ackerman in the UK is, with his pie in the sky, sends back, SSDV images, he sends back pictures. And I'm considering, sort of absorbing some of his code base. He's using a different code base than I have the LoRa libraries that I would use for the SP232, but I'm actually considering grabbing his base just to use the same decoding software that he's using to sort of standardize this. I don't see a reason for everybody doing LoRa to use a different protocol. That's sort of not helpful. So I may switch to what they're doing in the UK. But yeah, I think the LoRa is pretty cool, and LoRa also gives you bidirectional capability. So I was testing being able to send commands up to a payload through the LoRa module as well.
So one of the things I was doing with LoRa is using its lowest speed, which gives you the highest system gain. Okay, and that this works really, really well.
Yeah, I looked at that, and yeah, given that I was just sending, once every couple of seconds, like 5 seconds, I think, I was sending just basically GPS coordinates and some timestamps and a few things. I only needed to send like 40 or 50 byte packets, so I was able to set the speed to super slow, which gives you lots of additional gain.
If I can say something about the LoRa, and I'm just starting, but it was so promising. This little module is what it actually started with us. And the surprising thing is that this was mounted on somebody's bike, and it was received 108 kilometers further in Belgium.
Wow.
108 kilometers further. Yes.
Is that
we
a
only
T-beam?
have like.
Looks like a T-beam. Is
Yeah,
that
so
a
we got
T-beam? It looks like one.
because it even got a little battery thingy on the back if you want.
That's exactly the module I'm using. Yep.
But it's just, and when I picked up mine, I basically had it in front of my car, in the front seat of the car, driving through suburban areas, and it did receive 15 kilometers further. Unbelievable. With 100 milliwatts. Yeah.
Yeah, and they're like $25 on Banggood. They're
That's exactly, yeah.
wonderful. Yeah.
Mike, can you say a little bit about those LoRa modules and what they are and how they work?
Sure. I can't remember what the acronym LoRa stands for, but it's a spread spectrum protocol, and they make them in several different frequency ranges. I was using the 915 megahertz range. They also make some in 433 megahertz and 868 or something like that. And basically, it's a transmitter that's going to send packets back and forth. So with just a few lines of code that you can code in Arduino, you can send packets back and forth using the LoRa stuff. And there are parameters to set the data rate. And the lower the data rate you set, the higher the gain, essentially, because it does. I'm not sure if it's doing forward error correction or if it's just making every bit last a little bit longer while it's transmitting. So you just have a better chance of decoding. So Dave Ackerman in the UK for years now has been using LoRa modules to speak to a Raspberry Pi and calls it Pi in the Sky. And he uses the LoRa module to take images off the Raspberry Pi camera, packetize them and send them down via LoRa, and then reassemble them in flight. And so he's doing, basically live packet reassembly. And I think it takes, 15, 20, 30 seconds per packet to receive images from the flight, and he does that all flight long. So it's pretty cool. And he did bidirectional stuff with it. He even, I think at one point, set up a gateway so he could SSH to his Raspberry Pi in flight and log into it, which is a pretty showy demo.
So it's actually 150 kilohertz wide, the signal, and it's like the ultimate FT8 in the sky because it can be received minus 140 dB in the noise. And there was a German man that did an unauthorized, but later it was accepted, transmission over the QO100. So basically the man did 40,000 kilometers with his LoRa module. And the big satellite dish in Germany did see it in the noise then, but nobody else could hear or see any signal because it was so low. But that's why it's so amazing. It's just, yeah, you can pick it up in the noise where nobody else hears it. Yeah.
Yeah, I forgot to mention that. Yeah, just by nature of the protocol, it can be teased out of the noise, so you can't even hear the modulation. You wouldn't hear the modulation, but it's teasing the signal out of it. So yeah, they give you sort of, as I think it's minus 140 dB that it can actually start usefully decoding signal. So you can crank the data rate actually up fairly high and still decode signal based on that. I was super conservative with mine because I just didn't need the data rate. But if I start deciding to send images down, then yeah, I would crank up the data rate. But for this first flight, I just wanted to get some indication of if I was receiving it reliably, and if I was, could I transmit up to it to send telecommands up to the payload. And again, my secondary receive site for that was the beam on the ground station that was pointed off in the wrong direction. And because it was a very directional beam, I was in a blind spot once the payload got downrange. So the on-campus receiver wasn't receiving or anyway. And if it did, it would have been giving incorrect coordinates because of the 12,000 meter bug. So you'll need that for yours, by the way, that code. So